The property that we're going to discuss today, some people call it the alternate segment theorem. In Bulgaria, we call it the peripheral angle theorem. Anyway, they all refer to the same thing, is that if you have a triangle like this one and you take the circumcircle and you take a tangent line at one of the points where one vertex of the triangle is, then what is this angle? How can we find this angle here? It turns out it equals this angle, and now we're going to prove it. So suppose now this angle is alpha, and this is the center of the circle, so this is a radius, and another radius. We know from the previous video that this is a right angle here, and so this angle must be 90 degrees minus alpha. Now from this isosceles triangle, we know that this angle is also 90 degrees minus alpha, and so this angle here is 2 times alpha. And now because this is the center of the circle and this angle is 2 times alpha, then this angle is half of that, so it is alpha. And that's it. This angle equals this angle. And similarly, for example, this angle here would equal this angle here, like that. This angle equals this angle, and this angle equals this angle. And the third angle here, which is gamma, again verifies that alpha plus beta plus gamma equals 180 degrees. Here's the full picture with all the angles marked. So we can see the three angles, alpha, beta, and gamma, for example, here. Notice that if we had a parallel line here, parallel to this side of the triangle, then we again would have had alpha, beta, gamma, but in the opposite direction. Like alpha would have been here and gamma would have been here. So the tangent line to the circle is basically reversing the alpha and the gamma, such that alpha comes on this side and gamma comes on this side. Another way you can remember which angle comes where is to see, for example, this angle alpha. Which arc of the circle does it correspond to? And so we have the tangent line, and then the alpha is defined also by this line. This segment defines this arc, and this arc corresponds to the angle that points towards the arc, which is alpha, the angle alpha here. So this angle corresponds to this arc, which is, again, this angle. And this angle also corresponds to the same arc, so therefore it's also alpha. And also we know if we continue this line here, that we essentially took a point and then drew two tangent lines like this and like this. And from the previous video, we know that the length of this segment equals the length of this segment. This triangle here is isosceles. So if one angle is alpha, the other should also be alpha. We're going to discuss two optional problems today. This is the first one. Suppose we have a triangle here, and it's circumcircle, and we draw the tangent line at this point, like this, and we intersect it with this line, like that. And this is the angle bisector of this angle of the triangle. So this angle equals this angle. And we need to prove that this triangle here, the one with the red vertices, is isosceles. So we need to prove that this equals this. And here's the solution. We're going to denote this angle by alpha, this angle by beta, and the other angle in the triangle by gamma. So each of the two small parts is gamma over 2. Now from the alternate segments theorem, we know that this angle here, so this angle corresponds to this arc, which is this angle. And so it must be equal to alpha. On the other hand, from this triangle here, know that this is alpha and this is gamma over 2, and so this angle here is 180 minus alpha minus gamma over 2. And therefore, the complementary angle here is just alpha plus gamma over 2. And this is it. We didn't even need to include beta in our calculations, because this angle is now gamma over 2 plus alpha, and this one is alpha plus gamma over 2, so they're the same angle. And therefore, this triangle is isosceles. The second problem goes like this. We have a line, and we have two circles that touch the line, respectively at this point and this point, and they intersect at this point and this point. Then we took this line, the line passing through these 2 points, and it intersects the circle here. Then we connect it like this and like this, and then we connect it also like this. And we need to prove that the two green angles are equal. So we need to prove that this is an angle bisector of this angle here. First step of the solution is to connect these 2 points. Then we need to notice that this angle here splits into 2 parts. One is this part, using this red point here, and the other part is this one. So the left part of the angle, because of the alternate segments theorem, it points towards this arc, so it must equal this angle here. And the right part, so this angle here, by the alternate segments theorem for this triangle, it corresponds to this arc, and so it must be equal to this angle. And so the green angle, the whole green angle here, equals this angle plus this angle. Maybe it's more clear from this picture now, but we need to prove that this angle here, the green angle, equals the sum of this angle and this angle. Now, since this quadrilateral here is cyclic, we know that this angle equals this angle. So the green angle here moves to here. And now take a look at this triangle. We know that this angle plus this angle is 180, and we know that the sum of the angles in the triangle is also 180. And so the sum of this angle and this angle is 180 minus this angle, which equals this angle. And so the green angle equals the sum of the two blue angles. So in conclusion, this angle equals this angle because of the cyclic quadrilateral. Then this angle equals the sum of this angle and this angle because of the sum of the angles in this triangle. This angle equals this angle, and this angle equals this angle, so their sum is this full angle. So this angle equals this angle, and so this is an angle bisector of the angle here.